Log on, tune in, find out. Another good idea from Cambridge.
Matti Lassas from Helsinki University of Helsinki. And he's one of the most productive persons in this field. Today he's going to talk about shredding as a hat, a cloaked wave amplifier. Please.
Thank you very much. And all the results I'm presenting here are done in collaboration with Alan Greenleaf, Jaroslav Kurilev, and Gunther Ullmann. And my idea is to explain some new applications of invisibility cloaking. So, invisibility cloaking is very closely related to inverse problems. So let me start from those. Let us start from the Calderon's inverse problem that deals on the conductivity equation. So U is the electrical voltage, and if there are no sources in the body, then and there is a matrix valued conductivity sigma depending on x, we have the conductivity equation. The inverse problem can be formulated in the following way. Let's consider boundary measurements. Assume that we can measure all Dirichlet and Neumann pairs of solutions, or physically speaking, all possible voltages and current configurations one can observe at the boundary. Like in this picture, we have a tank that one actually fills with water. Here are electrodes. One puts these electrodes to some voltages, measures the currents, and obtains one of this type of pair. And then one goes through all possible observations and tries to find this type of reconstruction. So invisibility cloaking is a special kind of counterexample for inverse problem. In 2003, with Greenleaf and Ullmann, we tried to look at the limitations of medical imaging, and we constructed a counterexample based on blow-up of a map. So the map maps this type of. We start from two-dimensional ball, and then of radius 2. We start from three-dimensional ball. So B2 is three-dimensional ball with radius 2, and we remove 1 point. And the idea is that 1 point is such a small object that it's practically invisible. Then one makes a radial stretching. One sets the radial variables, blows up this point, so transform this 1 point hole to larger hole. And one then defines here an Euclidean metric G. So this is just a standard Euclidean metric, and pushes it forward by using this formula in this map to this like annulus. So this is now three-dimensional annulus. And the idea is now that these structures are isometric, and we have created a hole. Then we go from Riemannian metric to conductivity. One could think that the conductivity equation is actually the equation for harmonic functions when we have non-trivial metric. So we use the canonical formula, how the metric defines the conductivity. Here we have determinant of the metric to power 1/2, and then inverse of the metric. And then inside here we define some metric or some conductivity. We can, for simplicity, I put here just now Euclidean conductivity in there. Now this blow-up map is singular, so it implies that if I look the conductivity that up is here, it becomes singular on this surface. Here in spherical coordinates I have written it. These sign terms here are just related to the singularities of the sign function are just related to the fact that spherical coordinates are singular at the north and south pole, so that is not true singularity. But here we have r minus 1, so when r goes to 1, the radius goes to 1, this eigenvalue of the conductivity matrix goes to 0, so it approaches like perfect isolator. So in this sense this is degenerate. But what happens for the currents in this layer? Currents go in this way, they go around this singular blow-up map also transforms to currents. So currents go around this centerpiece, and we can put anything here without changing the boundary measurements. But even more is true, namely all boundary measurements coincide with the measurements done for a homogeneous object. So from the boundary, whatever measurements you do for the conductivity equation, it looks like a homogeneous body with constant conductivity gamma is 1. Indeed, if one looks here is, for instance, how the currents would go, they would go along the geodesics, actually, along straight lines, if we have homogeneous current field, and it is transformed to this type of field. It goes around the body, and outside the compact domain, the currents are not changed. The rigorous result we proved was that if one looks solutions in Sobolev 1 sense, so Sobolev 1 smooth functions that satisfy this equation, then the Cauchy data pairs or all voltage current pairs that are measured at the boundary, they coincide. In the case when we take any object, cover it with this special singular conductivity sigma tilde, or alternatively we take just a homogeneous body with constant conductivity. And in two-dimensional case, the singularity of the metric was different, and this was analyzed by Kohn, Shen, Vogelius, and Weinstein, 2007. So when we were constructing these examples, we were just interested about limitations of imaging, medical imaging, and we wanted to look for mathematical counterexamples. So we were positively very surprised when in 2006 it turns out that physicists are suggesting to build up this type of devices. Namely, there were two seminal papers and same issue of Science by Leonhardt and Pendry, Schurig and Smith, where it was proposed that one could consider new materials called metamaterials to implement invisibility cloaks. Leonhardt's suggestion was based, or proposal to construct this type of device, was based on taking a non-trivial Riemannian surface, stretching it, and embedding it to Euclidean space. Pendry, Schurig, and Smith proposed construction based on a similar blow-up map that was used. I explained later. Explained before this map F, this blow-up map of radial coordinates, and the idea is now that then light rays go around the body, not only currents but light rays. So these were proposed for non-zero frequencies, and like in Ulf Leonhardt's talk, it was shown maybe a better picture on this construction that somehow this kind of material consisting of small loops, so that when one homogenizes this media, then for waves having given frequency, it approximates this type of metric. I would like to point out that, like you see in this picture, light rays here go travel longer path than they would travel in the Euclidean space. So if you would like to do this type of cloaking device in vacuum, then this type of construction would not work with all frequencies. So these materials used here are very dispersive. They work well with one frequency. But the idea is now that we have a map that describes what kind of material parameters like conductivity, permittivity, or permeability we need. And then the separate question is how to build up a material having these properties. There has been also other suggestions for cloaking based on the negative materials. Alu and Engheta have proposed taking a dielectric ball and putting, maybe the picture is not so good, and putting around it negative media so that the scattering is reduced very much. Milton and Nikorovici, they have proposed that one take this type of annulus for negative material and when a dielectric object comes close to it, it becomes invisible. So this is very different. This is exterior cloaking. Then Leonhard and Tück lately had an ingenious construction that is based on taking a ball that is actually a mirror, putting around it non-homogeneous media so that light rays, when they go into the body, they come out from the right direction. So this is like cloaking for light rays. Now in this talk I will look at a little bit different type of invisibility. One can think invisibility for rays when one is interested how light rays propagate, or one can speak about invisibility in waves, which means that you consider partial differential equations. And I will consider now approximative cloaks. One good point in doing this is one reason to consider these approximative cloaks is that these perfect cloaks are singular. So one has to work very hard to think what is the appropriate sense to define the solutions. For approximative cloaks, the materials are not singular, and there's no question the solutions can be defined in standard way. So how we do the approximative cloak? We just take the singular cloak where the material becomes singular and replace layer, radial rail from radial parameter goes from 1 to r, where r is close to 1. We replace this by Euclidean space. So we just remove the material that is singular and put there, or is close to singular, and put there Euclidean space. And this has been also studied by Kohn, Onofre, Weinstein, and Vogelius. We have actually been interested in more on somehow the presence of resonances that appear. This group has started they have studied how to remove these resonances, and also Ling and Zhou have studied this for Maxwell equations. So what we do, we define this kind of approximative cloaking metric depending on parameter r, so that we take the cloaking metric coming from the blow-up map in the layer where radial parameter is from r to 2. Inside we put just identity matrix, and outside we put this whole device inside a large ball having radius L. We put this whole device inside a large ball, and outside this we have Euclidean this identity metric. Okay, let me study now spectral problem for this metric. I will consider the Laplace-Beltrame operator and look waves having frequency omega, and I point out that this problem can be written in terms as an acoustic equation. This I still denote it by conductivity matrix sigma, but you can think that it is inverse of mass density. And here we have this determinant of the metric to power 1/2, and that is the inverse of the bulk modulus. So, and this kind of equations are the basis of the acoustic cloaks that have been constructed. That are very active study how to construct these kind of things. And I recall that inside the cloaked area, inside the ball of radius r, this inverse of mass density is identity, and bulk modulus is 1. And also outside the cloaking device we use the same parameters. Okay. So this is one way to make approximative cloaks, but those materials were now anisotropic. And I want to also study isotropic approximative cloaks. So what one does? Then one has anisotropic conductivity. One can approximate it by taking layers of isotropic media and putting layers on top of each other. So basically, if I look, I'd like to put very highly conducting materials like this. Here in the middle I have much less conducting, then the media behaves like anisotropic media. So we use this type of profiles I use radial, I put spherical layers. I use this type of scalar function, so real function times identity matrix. It varies slowly in this variable, and in this variable it is periodic. So here this has period 1, so this conductivity has periods epsilon. So we have spherical layers of thickness epsilon that are isotropic. So this type of cloaks approximate well a perfect cloak. So what happens? Let us look equations, acoustic equations for these approximative cloaks. So here are now rapidly varying isotropic conductivity. And I put some boundary value there. Now one can show that one can choose these approximation parameters, these r and epsilon n's. Here you see the different radial parameter in such a way that when n goes to infinity, when the approximation gets better and better, then assuming that we have no resonances, the solution converges weakly to this type of function. Now what is here? So outside the cloak, the solution coincides with the solution in the Euclidean space. Then in the layer where the invisibility device lies, so the layer from 2 to 1, here I have the solution in the Euclidean space composed with a diffeomorphism. So here is actually a picture that we would have. We start from the plane wave. Outside here we have just usual plane wave. There is a layer where I have stretched the plane wave, and inside the cloak the solution is 0. And this happens when the frequency squared is not the Neumann eigenvalue of the interior or the Dirichlet eigenvalue of the whole ball, this ball of radius L. So why we wanted to study these isotropic cloaks? The reason is that in inverse problems it's very typical that we jump from one physical system to another. And now I want to consider these results in context of quantum mechanics. So I will do the standard Liouville transformation. So what we do, we start this acoustic equation. We consider that this omega squared is the energy, E, and I introduce new function psi. It is the solution of the acoustic equation and multiply it with the square root of the conductivity. Then this psi function satisfies the Schrödinger equation with electric potential Vn, where Vn has this formula. And I emphasize this depends on this energy E. So this psi function, we have taken a smooth function, this u function that is here, and multiplied it with oscillating function. So it looks like this. Actually, there are quite many layers, but here I have put only few. And often I will consider this acoustic equation because the solutions are smooth here. So the idea is now that this gives as a recipe how to build up in principle quantum mechanical invisibility cloaks. So cloaks for matter waves. And remember that we somehow the last theorem when we said that everything goes well, it was in the case when we are not in the eigenvalue. So let's look what happens in the case when energy is the eigenvalue, Neumann eigenvalue of this interior here. Then when these approximative cloaks, we look what happens when we make better and better approximations. We see that the eigenvalues of these equations, they converge to E And if you normalize these eigenfunctions correctly, the eigenfunctions converge to a function that in the interior coincides with the Neumann eigenvalue, Neumann eigenfunction in the interior and is 0 in the exterior. This is actually somehow the solution in the case when you have a perfect invisibility cloak, and there, because the equations are singular, in the sense that the coefficients are singular, there appears the Neumann boundary condition. And actually, if you know somehow serious Harry Potter fans, you can ask from them that what Harry Potter would see if he is inside the invisibility cloak. And the answer is that in usual cases, if you don't do anything special, you see the Neumann boundary condition, that is the mirror. And now one of the goals is to somehow change this, what is going on here. But let's first look cloaking. So now we know that when n is large, there are solutions that look almost like this. So they are large inside, and here when n is large but not infinity, the solution is non-zero. So what this means for the inverse problem or imaging? If you make boundary measurements for some object that has resonance, this kind of resonance can be very clearly seen in the measurements. Mainly, when you somehow do measurements close to the resonance in a frequency, then it's the response that you get from the object is very, very strong. So when we are close to the resonance, cloaking must fail. We very clearly see that something is in there that resonates. Now we have two effects. First, we saw that these eigenvalues, so eigenfunctions, they propagated inside. So the waves propagate inside the domain. And also we have other event, the cloaking fails. We can ask which one happens first. Is it possible to tune this construction in such a way that cloaking happens, but the waves propagate inside? Answer is actually yes. And to do this type of tuning, we will put inside here in the in the interior, we will put a potential. Okay, we put very simple potential inside the cloak. Piecewise constant radially symmetric potential. It depends on two parameters, tau1 and tau2, and both of these variables also depend on n. So in the small ball of radius 1/4, we put constant potential tau1, and in layer around it we put constant potential tau2. And this is now our equation. We have this basically cloaking potential and then the interior potential. And the idea will be that we will assume that we fix n, how good approximations we use energy, and then we fix this parameter. And then we will choose the interior, the potential in the close to origin in such a way that the waves propagate into the medium. And we call this potential that we have obtained the Schrödinger hat potential. The idea is that hat is something that you can put inside, so you can put something inside the hat, and I will show that this kind of events happen. It is just a kind of storage that we construct. Even though it's a little technical, let me explain how this parameter tau1 is chosen, because this is the crux of the matter. Actually, this is also extremely simple. Just looks at the technical. So let's look radially symmetric solutions for the acoustic this acoustic equation. Outside the invisibility device, this is just the Euclidean-Helmholtz equation. The solution has two terms. It is sum of a Bessel function j 0 and Hankel function h0. And let's somehow now consider the case when the approximative cloak works as perfectly as we could wish. That this term 1 is, that b is 0. And let's see what happens then. So we have a radially symmetric function satisfying this equation. I just used right, 2 and 2 and both of these variables also depend on n. So we have this potential that we have obtained the Schrödinger hat potential. this in radial coordinates, and I get the second order ordinary differential equation. And then I ask him that the solution looks like Bessel function here outside the cloak, from 2 to 3 here in this picture. So I put here initial data up to a multiplication with a constant. I can assume that Dirichlet data is Dirichlet data of the Bessel function, and Neumann data is the Neumann data of the Bessel function. Then I have an initial boundary value, initial value problem for an ordinary differential equation. I solve it. Here I know that the solution must coincide with the Bessel function. Then I get to the invisibility layer. There I solve this equation, and I know what the solution is. It will be the Bessel function computed in the point that where we have stretched through radial coordinates. So the solution looks inside the cloak from 2 to 1. It looks like this. It just oscillates a bit, and when it comes to the interior, it has value 1, and then it so it has value 1, and then it we can show that it has actually Neumann, almost Neumann boundary value. So derivative is 0. So then we just solve it. We had that inside we have a constant potential. So for each parameter tau 2, we can solve this equation. And then for each tau 1, we can solve this equation. Finally, we obtain some solution, and we compute its derivative at 0. So if the derivative is 0, at 0 is 0, then this defines the three-dimensional smooth function. We can rotate it. So let's choose the interior parameter in such a way that this condition is valid. And now we also had here these three parameters. And how we think this? If we choose the large tau 2, then we have here like a potential wall, and then tau 1 might be a potential well. So we have a structure where we have a potential well. Around it we have a wall. This almost resonates, and around this we have the invisibility cloaking potential. And now the solutions, they propagate inside to the cloak. So the thing here is that when we just assume that the cloak behaves optimally outside the domain, so that this term only, well, far from the invisibility device, then the waves propagate inside. So let's now look what this means for the boundary value problem. For the boundary value problem, when we choose parameters in this way, waves propagate nicely in. So if I look solution, this psi in is like incident field. So we have an Euclidean space, we look a boundary value problem, and then we add here the Schrödinger hat potential. When n goes to infinity, the solutions behave in this way. So outside the support of the Schrödinger hat potential, this limit coincides with the empty space solution, the incident wave. Then in the layer where the invisibility device is supported, we have again the incident wave supported, computed composed with the diffeomorphism. And here is some parameter just comes from this Liouville transformation. It's just bounded parameter, it's not very interesting. But inside we have the interior eigenfunction times the value that the incident field would have at 0. And I recall that this inside eigenfunction can grow to have very, very large values. And so basically we have the whole wave inside here is multiplied with the incident value, the value of the incident field at single point. So this is a little bit like quantum mechanical sensor. Let's look this picture a little differently, so it can look like this. So here we have just here the solution is the same as in the Euclidean space. Here it can be highly concentrated if the parameters are chosen correctly. Because this happens for the boundary values, the same happens for the scattering problems. Let's look at the whole space solutions with incident field. Satisfying this equation, we add the Schrödinger hat potential here. The scattered field satisfies our radiation condition. Here I have used plane wave that comes in, and the solution looks like this. So outside the support of the potential, there's no scattering field. Then there's layer where we have just stretched the solution and multiplied it with bounded factor, and in the interior it's a function that might have very large values, this interior eigenfunction. Let me show a video on this. Oops. Okay, so the plane wave, it's not in the loop. Plane wave comes in. Of course, if we have physical wave, it takes time before it finds the steady state, but when it is in time harmonic mode, solution looks like this. The wave is not disturbed, but there's a high concentration of wave inside here. I would like to think this in the way that we think that this device it like steals the probability mass that is passing it, put it to some invisible storage, and later returns it in the plane wave, and the total effect is such that the wave that comes out is not distorted. So this is kind of like storage for probability mass of this wave psi. So this was for the scattering problems. But it has very interesting effects when we look eigenvalue problems. Let's next look those, because then we can really like compute probabilities. What's the probability that the particle is somewhere? And I'm aiming for a kind of quantum mechanical illusion. We want to make an electron to disappear with a large probability using the Schrödinger hat potential. So again, I look two cases. I have a ball that is empty, and I put Dirichlet boundary condition. Then I have the same ball with Dirichlet boundary condition, and I put Schrödinger hat inside there. And then I look to eigen value problem. Energy E is now the Dirichlet eigenvalue of this, and it can be also made this potential such that so this is satisfied. So now, when we make better and better approximations, the wave behave again according to this formula. So here are the eigenfunctions. They coincide here near the boundary. Then there is more stretching, and then there might be very large concentration here. So the pictures look like, in this kind of representation, looks like this. So here, I mean, this could be very large, but I mean, even to make this type of pictures, I had to manipulate the color scale so that it looks sensible. So the eigenfunctions coincide here. This is the picture on one radial axis. So here they coincide. These are now non-normalized eigenfunctions, so the L2 norm is not 1. This red one is the empty space Green's function. This here is the Schrödinger hat eigenfunction. Sorry, both are eigenfunctions. And let's now look probabilities where the particle is, both for this empty space function and for the Schrödinger hat wave function. When S is a subset of this large ball, the probability that the particle is in the set S is just the integral of the square of the wave function divided by the normalization constant. And now normalization constants are different for the empty ball and the Schrödinger hat. solution, but the solutions coincide here. So what this means? If I look, first it means that in the Schrödinger hat, the particle is with very small probability observed outside the ball of radius 2. But second, if I look the conditional probabilities, assume that I observe it in this area. Because these functions coincide there, the conditional probability that I observe the particle, for instance, in the interval 4 to 6, under the condition that is observed outside the cloak, is same in empty ball and in the Schrödinger hat. So a little bit like playfully terms, I could say that this particle in the Schrödinger hat appears like a ghost of the empty space particle. Namely, it's observed very rarely, but when you observe it, it looks exactly like the empty space particle. This is actually true for all observables supported outside the cloak. Okay. Then some other observations. It's a little bit harder to analyze two-particle equations. So we used first order perturbation theory to understand what happens. And now let's think that the particles that I describe here are electrons, so they have a charge. Now the cloak concentrates the wave function inside the ball, and I can also, a little bit changing the many parameters here, concentrate the charge inside a small ball of radius delta, where delta is small. Now if I put two particles there, the Schrödinger hat tries to concentrate the charge around the origin, but two particles cannot come there because there is a repulsion. The Coulomb force forces them to go away from each other. So and what happens in first order perturbation theory? If I look the energy, that is the eigenvalue, how it changes in this two particle system. Now in the first order perturbation theory, I actually mean that the charge is a small parameter that I have put here. So there, the change of the energy when two particles are put inside there, in Schrödinger hat, it's the same that we would have in an empty ball where we put particles having much stronger charges of order delta to power -1/2. So it's very interesting that for one particle, the Schrödinger hat potential is invisible, but for two particles, it becomes very visible, like it's somehow making this repulsion force stronger. So now this has been basically just a mathematical model. So let me discuss shortly some possibilities how this kind of thing could be built. So quantum mechanical invisibility cloaks have been proposed, but the constructions are very hard. One construction by Chang has been that one takes extremely low temperature, put there optical lattice, so basically light, and put atoms inside this optical lattice. So this requires something like nano-Kelvin temperatures. Now we did this Liouville transformation, and it helps a lot because we could now look models, for instance, in solid state physics, and we found model that looks very similar to that is needed to Schrödinger hat. Namely, let's look semiconductor heterostructure of semiconductor, so structure where we have layers of semiconductors. There we use Gerard Bastard's envelope function model, which means that the wave function is approximated by, now use single band model, by slowly varying envelope function times the Prof function that varies very rapidly. And the envelope function satisfies Schrödinger equation. We use here Ben-Daniel-Duke Hamiltonian, which means that the effective mass is put in the equation to this place. And this very particular model has been suggested for this type of gallium aluminium arsenide heterostructures. And these structures are interesting in the sense that they look a little bit like this. They are atoms that can be replaced by other atoms. So this means that we can create a structure that varies smoothly. And actually, in this very particular type of heterostructure, here is the dispersion diagram of this this gallium arsenide. Here, close to the edge of the conduction band, the gamma point here, this model has been suggested by several authors. And now, this type of equation, where the effective mass varies and the electric potential varies, if you put sufficiently many layers, you could approximate the model where this becomes 1, and this varies as the Schrödinger hat potential. So this theory suggests that we could approximate the Schrödinger hat potential by using spherical layers of semiconductors, where the layers of the semiconductors have correctly chosen thicknesses. And the point is that because of this Liouville transformation, the approximation becomes better when the size of the structure is made larger. Unfortunately, this theory that we use to somehow prove these results for Schrödinger hat, it just says about the limit. At this moment, we know only that at the limit it goes to the correct model. But the question how many layers one would need, we don't have any estimate for that. Then about one other comment for this kind of models, and the fact that these semiconductors, this invisibility cloaking potentials work very well only close to given energy, because the medium is dispersive. Now this Liouville transformation that we did was involved energy, so this means that also this construction that we did works with some energy only. But in the semiconductors, this seems not to be so serious issue if you go to low temperatures, because of the following reason. If I look at the density function of the energies of the electrons, it is product of two factors. The density of the states, that looks like this. So here is the conduction band, looks like this. So it is basically energy minus this conduction, the edge of the conduction band energy. It's square root, like here. This density of states is multiplied with the Fermi-Dirac distribution. That is here. It looks like this. So when temperature T is small, this is basically exponential function. So this means that this density function of energies obeys very closely the gamma distribution. And the gamma distribution has variance that is proportional to temperature to second power. So if you go to quite low temperatures, then all electrons in the medium are very close to this energy level. So building up a Schrödinger hat potential that is planned, engineered for this energy level, would hopefully work. Okay. Yes, finally, I would like to make a short comment, because this is typical transformation optics construction. And so transformation optics just means that if we take diffeomorphic physical models, then the solutions are the same up to a diffeomorphism. And there has been numerous different somehow suggestions to build up different type of devices, different type of cloaking devices. I don't put there the authors because there are so many. Then we have been proposing like electromagnetic wormhole devices. One has proposed perfect absorbers, super lenses, and Leonhard has proposed recently this perfect imaging devices. And also previously we proposed for acoustic perfect sensors that are very close to Alu and Enghetas, this type of plasmonic cloaked sensors. And so because this transformation optics principle is very closely related to inverse problems, where we try to find out objects within a modular diffeomorphism, and also theory of many of these devices is based on partial differential equations with singular coefficients. There are extreme somehow need for mathematical work to analyze how rigorously to define these models, because it seems that rigorously defined models behave very well when those are approximated, much better than ad hoc constructions. And I end for this. Thank you very much.
There are some questions, comments?
So if you want to approximate your anisotropic structures with isotropic ones, that obviously will only depend, also will only work for a certain wavelength, doesn't it? So
you mean mathematically or
just bigger? So you fix your frequency,
yes,
and you design the layers such that for that frequency you can approximate the anisotropic.
I think it's a mathematical theory. Now, if we assume that the isotropic pieces are not dispersive, I mean, then the limit goes works for all frequencies.
For all frequencies.
Yes.
All large. Because there's no frequency in EIT, right? So
Sorry?
there's no frequency around
That's
the
true,
EIT.
yes. But I mean, if I look at this type of like Helmholtz equation, that
But obviously, so they have to be significantly smaller than the wavelength. So there is frequency, the hidden frequency depends in the way that they have to be small.
that's true, yes. They're basically this kind of homogeneous theory. It like requires that the parameter size goes to 0. That's actually a very interesting point, because so this construction was not based now on this kind of negative materials, but in the study of negative materials, I have been discussing with some engineers. Now the question that when you really get to this size to go to 0, it's extremely hard to make materials that resonate if at a given frequency if the size of the material goes to 0. And that's why somehow one engineer said to me that all mathematical homogeneous theory is useless. So there is very much somehow need to develop techniques where we mathematically understand homogeneity. Yeah.
Maybe a practical question. So when you talk about the electrons, so what is their wavelength? So you know what the distribution of these electrons is, and
Yes.
into wavelengths. So what is the size of the wavelengths you need, and from this you can infer what structure size you need for your different layers of semiconductors and so.
Yeah, actually for this yes. So this type of approximation, when we want to make the approximation better, then one has to increase the size of the device, but also the energy has to go smaller. So actually we are considering
just very useful order of magnitude. So what kind of structures do you need? So that obviously from that depends on whether people can build this.
Yes.
So if you need layers that are comparable to the size of an atom, then it's not going to work. If these layers are reasonably such that then can be engineered, then you could.
Yes. So let's. So the thing is now that this. So this the Schrödinger equation appears here for this envelope model.
Mm-hmm.
So this means that. So actually, this energy here that appears is somehow the distance from the conduction band edge. So so this now depends for how low temperatures you need to go, so that the electrodes are sufficiently close to this.
So you know those temperatures for.
We haven't made any this type of computers with asymmetric materials. I don't know what is the temperature, and we should run numerical simulations how many layers one really needs, and then somehow adjust the energy, find the energy level, and then to see for what type of temperatures you have to go. But I will hope that not to nanokelvins. That's very different physics then. So, yeah, not like that.
Very good question. Oh, do you have?
So you have this limit for the Helmholtz equation, and then after the Liouville transform, you have the limit of the Schrödinger equation.
Sure, yes.
Yes, what is the relation between these two? Are there a specific relation between these two limits?
And yeah, that is a curious thing that now the convergence is weak. If we are interested of the location of the particle, then we are interested of the wave function squared, and it converges to one limit, and it is different than the square of the weak limit of the wave functions. So it's quite delicate issue.
Yeah, it just occurred to me, when you use Lugol transformation in that way, the Schrodinger equation you get has no bound states. My guess is that after you add this hat function, maybe there are bound states. I'm guessing, I don't know.
Yes, yes, somehow on the limit, when like the approximation goes to to better and better, then we come to bound state. But I mean, before that, there is no we can.
Maybe it's better to continue the discussion by taking coffee. Yes, thank to the organizer and also the good questions and comments. Thank you very much.